Okay. So, welcome. Practical Deep Learning for Coders, Lesson 1. It's kind of Lesson 2 because there's a Lesson 0, and Lesson 0 is why do you need a GPU and how do you get it set up. So if you haven't got a GPU running yet, then go back and do that. Make sure that you can access a Jupyter Notebook and then you're ready to start the real Lesson 1. So if you're ready, you will be able to see something like this. In particular, hopefully you have gone to Notebook Tutorial. It's at the top. That's why I put a 00 here. As this grows, you'll see more and more files, but we'll keep Notebook Tutorial at the top. And you will have used your Jupyter Notebook to add 1 and 1 together, getting the expected result. Let's make that a bit bigger. And hopefully you've learnt these 4 keyboard shortcuts. So the basic idea is that your Jupyter Notebook has prose in it. It can have pictures in it. It can have charts in it. And most importantly, it can have code in it. Okay. So the code is in Python. How many people have used Python before? So nearly all of you. That's great. If you haven't used Python, that's totally okay. Right? It's a pretty easy language to pick up. But if you haven't used Python, this will feel a little bit more intimidating because the code that you're seeing will be unfamiliar to you. Yes, Rachel?
I was going to say, for people in the room, it's okay if they don't have the coding, right?
Oh, yeah.
Yeah.
No, because I'm trying to keep them both separate.
Sorry.
Yeah. Okay, well, now that we're here, I'll edit this bit out. So, as I say, there are things like this where people in the room, in person, this is one of those bits where it's like this is really for the MOOC audience, not for you. I think this will be the only time like this in the lesson where we've assumed you've got this set up. Thanks for the reminder. Okay. All right. So yeah, for those of you in the room or on FastAI Live, you can go back after this and make sure that you can get this running using the information in course v3.fast.ai. Okay. Great. Okay, so a Jupyter Notebook is a really interesting device for a data scientist because it kind of lets you run interactive experiments and it lets us give you not just a static piece of information, but it lets us give you something that you can actually interactively experiment with. So let me explain how we think works well to use these notebooks and to use this material. And this is based on the kind of last 3 years of experience we've had with the students who have gone through this course. First of all, it works pretty well just to watch a lesson end to end. Right? Don't try and follow along because it's not really designed to go at a speed where you can follow along. It's designed to be something where you just take in the information, you get a general sense of all of the pieces, how it all fits together. Right? And then you can go back and go through it more slowly, pausing in the video and trying things out, making sure that you can do the things that I'm doing, and that you can try and extend them to do things in your own way. Okay, so don't worry if things are zipping along faster than you can do them. That's normal. Also, don't try and stop and understand everything the first time. If you do understand everything the first time, good for you. But most people don't, particularly as the lessons go on. They get faster and they get more difficult. Okay. So at this point, we've got our notebooks going. We're ready to start doing deep learning. And so the main thing that hopefully you're going to agree at the end of this is that you can do deep learning, regardless of who you are. And we don't just mean do, we mean do at a very high level. We mean world-class practitioner level deep learning. Okay. So your main place to be looking for things is course v3.fast.ai. where you can find out how to get a GPU, other information, and you can also access our forums. Oopsie daisy. You can also access our forums, and on our forums you'll find things like how do you build a deep learning box yourself, and that's something that you can do after, later on once you've kind of got going. Who am I? So why should you listen to me? Well, maybe you shouldn't, but I'll try and justify why you should listen to me. I've been doing stuff with machine learning for over 25 years. I started out in management consulting, where actually initially I was, I think, McKinsey & Company's first analytical specialist, and went into general consulting. Ran a number of startups for a long time. Eventually became the president of Kaggle. But actually the thing I'm probably most proud of in my life is that I got to be the #1 ranked contestant in Kaggle competitions globally. So I think that's a good kind of practical, like, can you actually train a predictive model that predicts things? Pretty important aspect of data science. I then founded a company called Enlitic, which was the first kind of medical deep learning company. Nowadays, I'm on the faculty at University of San Francisco and also co-founder with Rachel of FastAI. So I've used machine learning throughout that time, and I guess I'm not really, although I am at USF at a university, I'm not really an academic type. I'm much more interested in using this tool to do useful things. Specifically, through FastAI, we are trying to help people use deep learning to do useful things through creating software to make deep learning easier to use at a very high level, through education, such as the thing you're watching now, through research, which is where we spend a very large amount of our time, which is researching to figure out how can you make deep learning easier to use at a very high level, which ends up in, as you'll see, in the software and the education, and by helping to build a community, which is mainly through the forums, so that practitioners can find each other and work together. So that's what we're doing. So this lesson, Practical Deep Learning for Coders, is kind of the starting point in this journey. It contains 7 lessons, each one's about 2 hours long. We're then expecting you to do about 8 to 10 hours of homework during the week. So it'll end up being something around 70 or 80 hours of work. I will say it varies a lot as to how much people put into this. I know a lot of people who work full-time on FastAI. Some folks who do the 2 parts can spend a whole year doing it really intensively. I know some folks watch the videos on double speed and never do any homework and come out the end of it with, a general sense of what's going on. So there's lots of different ways you can do this. But if you follow along with this kind of 10 hours a week or so approach for the 7 weeks, by the end, you will be able to build an image classification model on pictures that you choose that will work at a world-class level. You'll be able to classify text, again, using whatever data sets you're interested in. You'll be able to make predictions of kind of commercial applications like sales. You'll be able to build recommendation systems, such as the one used by Netflix. Not toy examples of any of these, but actually things that can come top 10 in Kaggle competitions, that can beat everything that's in the academic community, very, very high-level versions of these things. So that might surprise you, that the prerequisite here is literally 1 year of coding and high school math, but we have thousands of students now who have done this and shown it to be true. You will probably hear a lot of naysayers, less now than a couple of years ago than we started, but a lot of naysayers telling you that you can't do it, or that you shouldn't be doing it, or that deep learning's got all these problems. It's not perfect, but these are all things that people claim about deep learning, which are either pointless or untrue. It's not a black box. As you'll see, it's really great for interpreting what's going on. It does not need much data for most practical applications. You certainly don't need a PhD. Rachel has one, so it doesn't actually stop you from doing deep learning if you have a PhD. I certainly don't. I have a philosophy degree and nothing else. It can be used very widely for lots of different applications, not just for vision, which is where it's most well known. You don't need lots of hardware. You know, that 36 cent an hour server is more than enough to get world-class results for most problems. It's true that maybe this is not going to help you to build a sentient brain, but that's not our focus. Okay, so for all the people who say deep learning is not interesting because it's not really AI, not really a conversation that I'm interested in. We're focused on solving interesting real-world problems. What are you going to be able to do by the end of lesson 1? Well, this was an example from Nikhil, who's actually in the audience now because he was in last year's course as well. This is an example of something he did, which is he downloaded 30 images of people playing cricket and people playing baseball and ran the code you'll see today and built a nearly perfect classifier of which is which. So it's kind of stuff that you can build with some fun hobby examples like this, or you can try stuff, as we'll see, in the workplace that could be of direct commercial value. So this is the idea of where we're going to get to by the end of lesson 1. We're going to start by looking at code, which is very different to many of the academic courses. So for those of you who have a kind of an engineering or math or computer science background, this is very different to the approach where you start with lots and lots of theory, and then eventually you get to a postgraduate degree and you finally are at the point where you can build something useful. We're going to learn to build the useful thing today. Okay. Now that means that at the end of today, you won't know all the theory. Okay. There will be lots of aspects of what we do that you don't know why or how it works. That's okay. You will learn why and how it works over the next 7 weeks. But for now, we've found that what works really well is to actually get your hands dirty coding, not focusing on theory, because there's still a lot of artisanship in deep learning, unfortunately. It's still a situation where people who are good practitioners have a really good feel for how to work with the code and how to work with the data, and you can only get that through experience. And so the best way to get that feel of how to get good models is to create lots of models, do lots of coding, and study them carefully. And Jupyter Notebook provides a really great way to study them. So let's try that. Let's try getting started. So to get started, you will open your Jupyter Notebook and you'll click on Lesson 1. Lesson 1, Pets. And it will pop open looking something like this. And so here it is. So you can run a cell in a Jupyter Notebook by clicking on it and pressing Run. But if you do so, everybody will know that you're not a real deep learning practitioner, because real deep learning practitioners know the keyboard shortcuts. And the keyboard shortcut is Shift-Enter. Given how often you have to run a cell, don't be going all the way up here, finding it, clicking it, just Shift-Enter. Okay, so type, Shift-Enter, type, Shift-Enter. Up and down to move around, to pick something to run, Shift-Enter to run it. Okay. So we're going to go through this quickly, and then later on, we're going to go back over it more carefully. So here's the quick version to get a sense of what's going on. So here we are in Lesson 1, and these 3 lines is what we start every notebook with. These things starting with % are special directives to Jupyter Notebook itself. They're not Python code. They're called magics, which is kind of a cool name. And these 3 directives, the details aren't very important, but basically it says, hey, if somebody changes the underlying library code while I'm running this, please reload it automatically. If somebody asks to plot something, then please plot it here in this Jupyter Notebook. So just put those 3 lines at the top of everything. The next 2 lines load up the FastAI library. What is the FastAI library? So it's a little bit confusing. FastAI with no dot is the name of our software, and then fast.ai with the dot is the name of our organization. So if you go to docs.fast.ai, this is the FastAI library. Okay, we'll learn more about it in a moment, but for now, just realize everything we are going to do is going to be using basically either FastAI or the thing that FastAI sits on top of, which is PyTorch. PyTorch is one of the most popular libraries for deep learning in the world. It's a bit newer than TensorFlow, so in a lot of ways it's more modern than TensorFlow. It's extremely fast-growing, extremely popular, and we use it because, we used to use TensorFlow a couple of years ago, and we found we can just do a lot more quickly with PyTorch. And then we have this software that sits on top of PyTorch and lets you do far more things, far more easily than you can with PyTorch alone. So it's a good combination. We'll be talking a lot about it. But for now, just know that you can use FastAI by doing two things. Importing star from FastAI, and then importing star from fastai.something, where something is the application you want. And currently FastAI supports 4 applications: computer vision, natural language text, tabular data, and collaborative filtering. Okay? And we're going to see lots of examples of all of those during the 7 weeks. So we're going to be doing some computer vision. At this point, if you are a Python software engineer, you are probably feeling sick because you've seen me go import star, which is something that you've all been told to never ever do. Okay? And there's very good reasons to not use import star in standard production code with most libraries. But you might have also seen, for those of you that have used something like MATLAB, it's kind of the opposite. Everything's there for you all the time. You don't even have to import things a lot of the time. It's kind of funny. We've got these two extremes of like, how do I code? You've got the scientific programming community that has one way, and then you've got the software engineering community that has the other. Both have really good reasons for doing things, and with the FastAI library, we actually support both approaches. In a Jupyter Notebook, where you want to be able to quickly, interactively try stuff out, you don't want to be constantly going back up to the top and importing more stuff and trying to figure out where things are. You want to be able to use lots of tab complete, be very experimental, so import star is great. Then when you're building stuff in production, you can do the normal PEP 8 style, proper software engineering practices. So don't worry when you see me doing stuff which at your workplace is frowned upon. Okay, this is a different style of coding. It's not that there are no rules in data science programming, it's that the rules are different, right? When you're training models, the most important thing is to be able to interactively experiment quickly. Okay, so you'll see we use a lot of very different processes, styles, and stuff to what you're used to, but they're there for a reason, and you'll learn about them over time. You can choose to use a similar approach or not. It's entirely up to you. The other thing to mention is that the FastAI libraries designed in a very interesting modular way, and you'll find over time that when you do use import star, there's far less clobbering of things than you might expect. It's all explicitly designed to allow you to pull in things and use them quickly without having problems. Okay, so we're going to look at some data. And there's 2 main places that we'll be tending to get data from for the course. One is from academic data sets. Academic data sets are really important, they're really interesting. They're things where academics spend a lot of time curating and gathering a data set so that they can show how well different kinds of approaches work with that data. And the idea is they try to design data sets that are challenging in some way and require some kind of breakthrough to do them well. So we're going to be starting with an academic data set called the PET data set. The other kind of data set we'll be using during the course is data sets from the Kaggle competitions platform. Both academic data sets and Kaggle data sets are interesting for us, particularly because they provide strong baselines. That is to say, you want to know if you're doing a good job. So with Kaggle data sets that have come from a competition, you can actually submit your results to Kaggle and see how well would you have gone in that competition. And if you can get in about the top 10%, then I'd say you're doing pretty well. For academic data sets, academics write down in papers what the state of the art is. So how well did they go with using models on that data set? Okay. So this is what we're going to do. We're going to try and create models that get right up towards the top of Kaggle competitions, preferably actually in the top 10, not just the top 10%, or that meet or exceed academic state-of-the-art published results. When you use an academic data set, it's important to cite it. So you'll see here there's a link to the paper that it's from. You definitely don't need to read that paper right now, but if you're interested in learning more about it and why it was created and how it was created, all the details are there. So in this case, this is a pretty difficult challenge. The PET data set is going to ask us to distinguish between 37 different categories of dog breed and cat breed. So that's really hard. In fact, every course until this one, we've used a different data set, which is one where you just have to decide is something a dog or is it a cat. So you've got a 50-50 chance right away, right? And dogs and cats look really different, whereas lots of dog breeds and cat breeds look pretty much the same. So why have we changed our data set? We've got to the point now where deep learning is so fast and so easy that the dogs versus cats problem, which a few years ago was considered extremely difficult, 80% accuracy was the state of the art, it's now too easy. Our models were basically getting everything right all the time without any tuning, and so there weren't really a lot of opportunities for me to show you how to do more sophisticated stuff. So we've picked a harder problem this year. So this is the first class where we're going to be learning how to do this difficult problem. And this kind of thing where you have to distinguish between similar categories is called, in the academic context, it's called fine-grained classification. So we're going to do the fine-grained classification task of figuring out a particular kind of pet. And so the first thing we have to do is download and extract the data that we want. We're going to be using this function called untar data, which will download it automatically and will untar it automatically. AWS has been kind enough to give us lots of space and bandwidth for these data sets, so they'll download super quickly for you. And so the first question then would be, how do I know what untar data does? So you can just type help, and you will find out what module did it come from, because since we imported star, we don't necessarily know that. What does it do? And something you might not have seen before, even if you're an experienced programmer, is what exactly do you pass to it? You're probably used to seeing the names, URL, file name, destination, but you might not be used to seeing these bits. These bits are types, okay? And if you've used a type programming language, you'll be used to seeing them, but Python programmers are less used to it. But if you think about it, you don't actually know how to use a function unless you know what type each thing is that you're providing it. So we make sure that we give you that type information directly here in the help. So in this case, the URL is a string, and the file name is either, union means either a path or a string, and it defaults to nothing. And the destination is either a path or a string, and it defaults to nothing. So we'll learn more shortly about how to get more documentation about the details of this. But for now, we can see we don't have to pass in a file name or a destination. It'll figure them out for us from the URL. So, and for all the data sets we'll be using in the course, we already have constants defined for all of them, right? So in this URLs module, or class actually, you can see that's where it's going to grab it from. Okay, so it's going to download that to some convenient path and untar it for us, and will then return the value of path. Okay, and then in Jupyter Notebook, it's kind of handy. You can just write a variable on its own, right? And semicolon is just an end of statement marker in Python, so it's the same as doing this. You can write it on its own, and it prints it. You can also say print, right? But again, we're trying to do everything fast and interactively. So just write it, and here is the path where it's given us our data. Next time you run this, since you've already downloaded it, it won't download it again. Since you've already untarred it, it won't untar it again. So everything's kind of designed to be pretty automatic, pretty easy. There are some things in Python that are less convenient for interactive use than they should be. For example, when you do have a path object, seeing what's in it actually takes a lot more typing than I would like. So sometimes we add functionality into existing Python stuff. One of the things we do is we add an ls method to paths. So if you go path.ls, here is what's inside this path. So that's what we just downloaded. So when you try this yourself, you wait a couple of minutes for it to download, unzip, and then you can see what's in there. If you're an experienced Python programmer, you may not be familiar with this approach of using a slash like this. This is a really convenient function that's part of Python 3. It's functionality from something called pathlib. These are path objects. Path objects are much better to use than strings. That lets you basically create subpaths like this Doesn't matter if you're on Windows, Linux, Mac, it's always going to work exactly the same way. So here's a path to the images in that data set. All right, so if you're starting with a brand new data set, trying to do some deep learning on it, what do? Well, the first thing you would want to do is probably see what's in there. So we found that these are the directories that are in there. So what's in this? Images. There's a lot of functions in FastAI for you. There's one called getImageFiles that will just grab an array of all of the image files based on extension in a path. And so here you can see we've got lots of different files. Okay, so this is a pretty common way for computer vision data sets to get passed around, is that there's just one folder with a whole bunch of files in. So the interesting bit then is, how do we get the labels? So in machine learning, the labels refer to the thing we're trying to predict. And if we just eyeball this, we can immediately see that the labels are actually part of the file name. You see that, right? It's kind of like path/label_number extension. So we need to somehow get a list of these bits of each file name, and that will give us our labels. Because that's all you need to build a deep learning model. You need some pictures, so files containing the images, and you need some labels. So in FastAI, this is made really easy. There's a object called ImageDataBunch, and an ImageDataBunch represents all of the data you need to build a model. And there's basically some factory methods which try to make it really easy for you to create that data bunch. We'll talk more about this shortly, but a training set and a validation set with images and labels for you. Now in this case, we can see we need to extract the labels from the names. Okay, so we're going to use from name RE. So for those of you that use Python, you'll know RE is the module in Python that does regular expressions, things that's really useful for extracting text. I just went ahead and created the regular expression that would extract the label from this text. Okay, so those of you who are not familiar with regular expressions, super useful tool. It'd be very useful to spend some time figuring out how and why that particular regular expression is going to extract the label from this text. Okay, so with this factory method, we can basically say, okay, I've got this path containing images. This is a list of file names. Remember, I got them back here. This is the regular expression pattern that is going to be used to extract the label from the file name. We'll talk about transforms later. And then you also need to say, what size images do you want to work with? So that might seem weird. Why do I need to say what size images I want to work with? Because the images have a size. We can see what size the images are. And I guess, honestly, this is a shortcoming of current deep learning technology, which is that a GPU has to apply the exact same instruction to a whole bunch of things at the same time in order to be fast. And so if the images are different shapes and sizes, it can't do that. Right? So we actually have to make all of the images the same shape and size. In part one of the course, we're always going to be making images square shapes. In part two, we'll learn how to use rectangles as well. It turns out to be surprisingly nuanced. Right? But pretty much everybody in pretty much all computer vision modeling, nearly all of it, uses this approach of square. And 224 by 224, for reasons we'll learn about, is an extremely common size that most models tend to use. So if you just use size equals 224, you're probably going to get pretty good results most of the time. And this is kind of the little bits of artisanship that I want to teach you folks, which is like what generally just works. Okay, so if you just use size equals 224, that'll generally just work for most things most of the time. So this is going to return a data bunch object. And in FastAI, everything you model with is going to be a data bunch object. We're going to learn all about them and what's in them and how do we look at them and so forth. But basically, a data bunch object contains 2 or 3 data sets. It contains your training data. We'll learn about this shortly. It'll contain your validation data, and optionally, it contains your test data. And for each of those, it contains your your images and your labels, or your texts and your labels, or your tabular data and your labels, or so forth. And that all sits there in this one place. Something we'll learn more about a little bit is normalization, but generally in nearly all machine learning tasks, you have to make all of your data about the same size, specifically about the same mean and about the same standard deviation. So there's a normalize function that we can use to normalize our data bunch in that way.
Getting a question.
Okay, Rachel, come and ask the question. Come over here. Thanks.
What does the function do if the image size is not 224?
Great. So this is what we're going to learn about shortly. Basically, this thing called transforms is used to do a number of things, and one of the things it does is to make something size 224. Let's take a look at a few pictures. Here are a few pictures of things from my data bunch. So you can see data.showBatch can be used to show me the contents of some of the contents in my data bunch. So this is going to be 3 by 3. And you can see roughly what's happened is that they all seem to have been kind of zoomed and cropped in a reasonably nice way. So basically what it'll do is something called, by default, center cropping, which means it'll kind of grab the middle bit and it'll also resize it. So we'll talk more about the details of this because it turns out to actually be quite important. But basically a combination of cropping and resizing is used. Something else we'll learn about is we also use this to do something called data augmentation. So there's actually some randomization in how much and where it crops and stuff like that. Okay, but that's the basic idea, is some cropping and some resizing. Often we also do some padding. So there's all kinds of different ways, and it depends on data augmentation, which we're going to learn about shortly.
And what does it mean to normalize the images?
So normalizing the images we're going to be learning more about later in the course, but in short it means that the pixel values, and we're going to be learning more about pixel values, the pixel values start out from 0 to 255, and some pixel values might tend to be really, well, I should say some channels, because there's red, green, and blue. So some channels might tend to be really bright, and some might tend to be really not bright at all, and some might vary a lot, and some might not vary much at all. It really helps train a deep learning model if each one of those red, green, and blue channels has a mean of 0 and a standard deviation of 1. Okay? We'll learn more about that. If you haven't studied or don't remember means and standard deviations, we'll get back to some of that later. But that's the basic idea. That's what normalization does. If your data, and again, we'll learn much more about the details, but if your data is not normalized, it can be quite difficult for your model to train well. So if you do have trouble training a model, one thing to check is that you've normalized it.
As GPU men will be in power of 2, doesn't size 256 sound more practical, considering GPU utilization?
So we're going to be getting into that shortly, but the brief answer is that the models are designed so that the final layer is of size 7 by 7. So we actually want something where if you go 7 times 2 a bunch of times, then you end up with something that's a good size. Yeah, all of these details we are going to get to, but the key thing is I wanted to get you training a model as quickly as possible. But one of the most important things to be a really good practitioner is to be able to look at your data. Okay, so it's really important to remember to go data.showBatch and take a look. It's surprising how often when you actually look at the data set you've been given that you realize it's got weird black borders on it, or some of the things have text covering up some of it, or some of it's rotated in odd ways. So make sure you take a look. Okay. And then the other thing we want to do is not just look at the pictures, but also look at the labels. And so all of the possible label names are called your classes. Right? So in the data bunch, you can print out your data.classes. And so here they are. That's all of the possible labels that we found by using that regular expression on the file names. And we learned earlier on in that prose I wrote at the top that there are 37 possible categories. And so just checking length, data.classes, it is indeed 37. A data bunch will always have a property called C, and that property called C, the technical details we'll kind of get to later, but for now you can kind of think of it as being the number of classes. For things like regression problems and multi-label classification and stuff, that's not exactly accurate, but it'll do for now. It's important to know that data.c is a really important piece of information that is something like, or at least for classification problems, it is the number of classes. All right, believe it or not, we're now ready to train a model. And so a model is trained in FastAI using something called a learner. And just like a data bunch is a general FastAI concept for your data, and from there are subclasses for particular applications, like image data bunch. A learner is a general concept for things that can learn to fit a model, and from that there are various subclasses to make things easier, and in particular there's one called convlearner, which is something that will create a convolutional neural network for you. And we'll be learning a lot about that over the next few lessons. But for now, just know that to create a learner for a convolutional neural network, you just have to tell it two things. The first is, what's your data? And not surprisingly, it takes a data bunch. And the second thing you need to tell it is, what's your model? Or what's your architecture? So as we'll learn, there are lots of different ways of constructing a convolutional neural network. But for now, the most important thing for you to know is that there's a particular kind of model called a ResNet, which works extremely well nearly all the time. And so for a while at least, you really only need to be choosing between two things, which is what size ResNet do you want? Okay, just basically, how big is it? And we'll learn all about the details of what that means. But there's one called a ResNet 34, and there's one called a ResNet 50. And so when we're getting started with something, I'll pick the smaller one because it'll train faster. So that's kind of it. That's as much as you need to know to be a pretty good practitioner about architectures for now, which is that there's two architectures, or two variants of one architecture that work pretty well, ResNet 34 and ResNet 50. Start with the smaller one and see if it's good enough. So that is all the information we need to create a convolutional neural network learner. There's one other thing I'm going to give it though, which is a list of metrics. Metrics are literally just things that get printed out as it's training. So I'm saying I would like you to print out the error rate, please. Now you can see the first time I ran this on a newly installed box, it downloaded something. What's it downloading? It's downloading the ResNet 34 pre-trained weights. Now what this means is that this particular model has actually already been trained for a particular task. And that particular task is that it was trained on looking at about 1.5 million pictures of all kinds of different things, 1,000 different categories of things, using a data set called ImageNet. And so we can download those pre-trained weights so that we don't start with a model that knows nothing about anything, but we actually start with a model that knows how to recognize the 1,000 categories of things in ImageNet. Now, I'm not sure, but I don't think all of these 37 categories of pet were in ImageNet, but there were certainly some kinds of dog, and there were certainly some kinds of cat. So this pre-trained model already knows quite a little bit about what pets look like, and it certainly knows quite a lot about what animals look like and what photos look like. So the idea is that we don't start with a model that knows nothing at all, but we start by downloading a model that knows something about recognizing images already. So it downloads for us automatically the first time we use it, a pre-trained model. And then from now on, it won't need to download it again. It'll just use the one we've got. This is really important. We're going to learn a lot about this. It's kind of the focus of the whole course, which is how to do, this is called transfer learning. How to take a model that already knows how to do something pretty well and make it so that it can do your thing really well. We take a pre-trained model and then we fit it so that instead of predicting the 1,000 categories of ImageNet with the ImageNet data, it predicts the 37 categories of pets using your pet data. And it turns out that by doing this, you can train models in 1/100th or less of the time of regular model training with 1/100th or less of the data of regular model training. In fact, potentially many thousands of times less. Remember I showed you the slide of Nikhil's Lesson 1 project from last year? He used 30 images. And there's not cricket and baseball images in ImageNet, right? But it just turns out that ImageNet's already so good at recognizing things in the world that just 30 examples of people playing baseball and cricket was enough to build a nearly perfect classifier. Okay. Now, you would naturally be potentially saying, well, wait a minute, how do you know that it can actually recognize pictures of people playing cricket versus baseball in general? Maybe it just learned to recognize those 30. Maybe it's just cheating, right? And that's called overfitting. We'll be talking a lot about that during this course, right? But overfitting is where you don't learn to recognize pictures of, say, cricket versus baseball, but just these particular cricketers and these particular photos and these particular baseball players and these particular photos. We have to make sure that we don't overfit. And so the way we do that is using something called a validation set. A validation set is a set of images that your model does not get to look at. And so these metrics, like in this case error rate, get printed out automatically using the validation set, a set of images that our model never got to see. When we created our data bunch, it automatically created a validation set for us. Okay? And we'll learn lots of ways of creating and using validation sets, but because we try to bake in all of the best practices, we actually make it nearly impossible for you not to use a validation set. Because if you're not using a validation set, you don't know if you're overfitting. Okay? So we always print out the metrics on a validation set, we always hold it out, we always make sure that the model doesn't touch it. That's all done for you. Okay? And that's all built into this data bunch object. So now that we have a conv learner, we can fit it. You can just use a method called fit, but in practice, you should nearly always use a method called fit one cycle. We'll learn more about this during the course, but in short, one cycle learning is a paper that was released, I'm trying to think, a few months ago, less than a year ago.
March?
So a few months ago, and it turned out to be dramatically better, both more accurate and faster than any previous approach. So again, I don't want to teach you how to do 2017 deep learning. Right? In 2018, the best way to fit models is to use something called one cycle. We'll learn all about it, but for now, just know you should probably type learn.fit one cycle. Right? If you forget how to type it, you can start typing a few letters and hit tab, okay, and you'll get a list of potential options. Right? And then if you forget what to pass it, you can press Shift tab, and it'll show you exactly what to pass it. So you don't actually have to type help. And again, this is kind of nice that we have all the types here because we can see cycle length, we'll learn more about what that is shortly, is an integer, and then max learning rate could either be a float or a collection or whatever, and so forth. And you can see that momentums will default to this tuple, so on and so forth. Okay, so for now, just know that this number 4 basically decides how many times do we go through the entire data set? How many times do we show the data set to the model so that it can learn from it? Each time it sees a picture, it's going to get a little bit better, but it's going to take time, and it means it could overfit. If it sees the same picture too many times, it'll just learn to recognize that picture, not pets in general. We'll learn all about how to tune this number during the next couple of lessons, but starting out with 4 is a pretty good start, just to see how it goes. And you can actually see after 4 epochs, or 4 cycles, we've got an error rate of 6%. So a natural question is, how long did that take? That took 1 minute and 56 seconds. Right. So we're paying, 60 cents an hour. We just paid for 2 minutes of time. I mean, we actually pay for the whole time that it's on and running, but we use 2 minutes of compute time. And we got an error rate of 6%. So 94% of the time, we correctly picked the exact right one of those 94 dog and cat breeds, which feels pretty good to me. But to get a sense of how good it is, maybe we should go back and look at the paper. Just remember, I said the nice thing about using academic papers or Kaggle data sets is we can compare our solution to whatever the best people in Kaggle did or whatever the academics did. So this particular data set of pet breeds is from 2012. And if I scroll through the paper, you'll generally find in any academic paper there'll be a section called experiments about 2/3 of the way through. And if you find the section on experiments, then you can find the section on accuracy. And they've got lots of different models. And their models, as you'll read about in the paper, are extremely kind of pet specific. They learn something about how pet heads look and how pet bodies look and pet images in general look, and they combine them all together. And once they use all of this complex code and math, they got an accuracy of 59%. Okay, so in 2012, this highly pet-specific analysis got an accuracy of 59%. And these were the top researchers from Oxford University. Today, in 2018, with basically, if you go back and look at actually how much code we just wrote, it's about 3 lines of code. The other stuff is just printing out things to see what we're doing. We got 94%, so 6% error. So like that gives you a sense of, how far we've come with deep learning, and particularly with PyTorch and FastAI, how easy things are. Yeah. So before we take a break, I just want to check to see if we've got any. And just remember, if you're in the audience and you see a question that you want asked, please click the love heart next to it so that Rachel knows that you want to hear about it. Also, if there is something with 6 likes and Rachel didn't notice it, which is quite possible, just quote it in a reply and say, hey, Rachel, this one's got 6 likes. Okay, so what we're going to do is we're going to take a 8-minute break. So we'll come back at 8:05. So where we got to was we just trained a model. We don't exactly know what that involved or how it happened, but we do know that with 3 or 4 lines of code, we built something which smashed the accuracy of the state-of-the-art of 2012. 6% error certainly sounds like pretty impressive for something that can recognize different dog breeds and cat breeds. But we don't really know why it works, but we will. That's okay. Right? And in terms of getting the most out of this course, we very, very regularly hear after the course is finished the same basic feedback, which this is literally copy and pasted from the forum. I fell into the habit of watching the lectures too much and Googling too much about concepts without running the code. At first I thought I should just read it and then research the theory. Okay? And we keep hearing people saying, my number one regret is I just spent 70 hours doing that. And at the very end, I started running the code, and it turned out I learned a lot more. So please, run the code. Really run the code. I should have spent the majority of my time on the actual code in the notebooks, running it, seeing what goes in, and seeing what comes out. So your most important skills to practice are learning, and we're going to show you how to do this in a lot more detail, but understanding what goes in and what goes out. So we've already seen an example of looking at what goes in, which is data.showBatch. And that's going to show you examples of labels and images. And so next, we're going to be seeing how to look at what came out. Right? So that's the most important thing to study. As I said, the reason we've been able to do this so quickly is heavily because of the FastAI library. Now, the FastAI library is pretty new, but it's already getting an extraordinary amount of traction. As you've seen, all of the major cloud providers either support it or are about to support it. A lot of researchers are starting to use it. It's making a lot of things a lot easier, but it's also making new things possible. And so really understanding the FastAI software is something which is going to take you a long way. And the best way to really understand the FastAI software well is by using the FastAI documentation. And we'll be learning more about the FastAI documentation shortly. So how does it compare? I mean, there's really only one major other piece of software like FastAI that is something that tries to make deep learning easy to use. and that's Keras. Keras is a really terrific piece of software. We actually used it for the previous courses until we switched to FastAI. It runs on top of TensorFlow. It was kind of the gold standard for making deep learning easy to use before, but life is much easier with FastAI. So if you look, for example, at the last year's course exercise, which is getting dogs versus cats, FastAI lets you get much more accurate, less than half the error on a validation set, of course. Training time is less than half the time. Lines of code is about a sixth of the lines of code. And the lines of code are more important than you might realize, because those 31 lines of Keras code involve you making a lot of decisions, setting lots of parameters, doing lots of configuration. So that's all stuff where you have to know how to set those things to get kind of best practice results. Whereas these 5 lines of code, anytime we know what to do for you, we do it for you. Anytime we can pick a good default, we pick it for you. Okay? So hopefully you'll find this a really useful library, not just for learning deep learning, but for taking it a very long way. How far can you take it? Well, as you'll see, all of the research that we do at FastAI uses the library. And an example of the research we did, which was recently featured in Wired, describes a new breakthrough in natural language processing, which people are calling the ImageNet moment, which is basically we broke a new state-of-the-art result in text classification, which OpenAI then built on top of our paper to do with more compute and more data and some different tasks to take it even further. This is an example of something that we've done in the last 6 months in conjunction actually with my colleague Sebastian Ruder. An example of something that's being built in the FastAI library, and you're going to learn how to use this brand new model in 3 lessons time. And you're actually going to get this exact result from this exact paper yourself. Another example, one of our alums, Hamel Hussain, who you'll come across on the forum plenty because he's a great guy, very active, built a new system for natural language semantic code search. You can find it on GitHub, where you can actually type in English sentences and find snippets of code that do the thing you ask for. And again, that's being built with the FastAI library using the techniques you'll be learning in the next 7 weeks.
In production.
In production, yeah. Well, it's. I think at this stage it's part of their experiments platform, so it's kind of pre-production, I guess. And so the best place to learn about these things and get involved in these things is on the forums, where as well as categories for each part of the course, there's also a general category for deep learning where people talk about research papers, applications, so on and so forth. So even though today we're kind of going to focus on a small number of lines of code to do a particular thing, which is image classification, and we're not learning much math or theory or whatever, over these 7 weeks, and then part 2, another 7 weeks, we're going to go deeper and deeper and deeper. And so where can that take you? I want to give you some examples. That there is Sarah Hooker. She did our first course a couple of years ago. Her background was economics. Didn't have a background in coding, math, computer science. I think she started learning to code 2 years before she took our course. She helped develop something she started a nonprofit called Delta Analytics. They helped build this amazing system where they attached old mobile phones to trees in the Kenyan rainforests and used it to listen for chainsaw noises, and then they used deep learning to figure out when there was a chainsaw being used, and then they had a system set up to alert rangers to go out and stop illegal deforestation in the rainforests. So that was something that she was doing while she was in the course as part of her kind of class projects. What's she doing now? She is now a Google Brain researcher, which I guess is one of the top, if not the top place to do deep learning. She's just been publishing some papers. Now she is going to Africa to set up Google Brain's first deep learning AI research center in Africa. Now I'll say, like, she worked her ass off. You know, she really, really invested in this course, not just doing all of the assignments, but also going out and reading Ian Goodfellow's book and doing lots of other things, but it really shows where somebody who has no computer science or math background at all can be now one of the world's top deep learning researchers and doing very valuable work. Another example from our most recent course, Christine Payne, she is now at OpenAI. And you can find her post and actually listen to her music samples she actually built something to do automatically create chamber music compositions that you can play and you can listen to online. And so, again, it's her background, math and computer science. Actually, that's her there, classical pianist. Now, I will say she's not your average classical pianist. She's a classical pianist who also has a master's in medical research from Stanford and studied neuroscience and was a high-performance computing expert at D.E. Shaw and was valedictorian at Princeton. Anyway, she, very annoying person, good at everything she does. But, I think it's really cool to see how a kind of a domain expert, in this case the domain of playing piano, can go through the FastAI course and come out the other end at, I guess OpenAI would be, of the three top research institutes, Google Brain and OpenAI would be two of them, probably along with DeepMind. And interestingly, actually, one of our other students, or I should say alumni of the course, recently interviewed her for a blog post series he's doing on top AI researchers. And she said one of the most important pieces of advice she got was from me. And she said the piece of advice was pick one project, do it really well, make it fantastic. Okay, so that was the piece of advice she found the most useful. And we're going to be talking a lot about you doing projects and making them fantastic during this course. Having said that, I don't really want you to go to AI or Google Brain. What I really want you to do is go back to your workplace or your passion project and apply these skills there, right? Let me give you an example. MIT released a deep learning course, and they highlighted in their announcement for this deep learning course this medical imaging example. And one of our students, Alex, who is a radiologist, said, you guys just showed a model overfitting. I can tell because I'm a radiologist, and this is not what this would look like on a chest film. This is what it should look like, and this, as a deep learning practitioner, this is how I know that this is what happened in your model. So Alex is combining his knowledge of radiology and his knowledge of deep learning to assess MIT's model from just two images very accurately, right? And so this is actually what I want most of you to be doing, is to take your domain expertise and combine it with the deep learning practical aspects that you'll learn in this course and bring them together like Alex is doing here. And so a lot of radiologists have actually gone through this course now and have built journal clubs and American Council of Radiology practice groups. There's a Data Science Institute at the ACR now and so forth, and Alex is one of the people who's providing kind of a lot of leadership in this area. I would love you to do the same kind of thing that Alex is doing, which is to really bring deep learning leadership into your industry, into your social impact project, whatever it is that you're trying to do. So another great example was Melissa Fabros, who was a English literature PhD. I think she studied like gendered language in English literature or something. And actually, Rachel in a previous job taught her to code, I think. And then she came into the FastAI course, and she helped Kiva, a micro-lending social impact organization, to build a system that can recognize faces. Why is that necessary? Well, we're going to be talking a lot about this. But because most AI researchers are white men, most computer vision software can only recognize white male faces effectively. In fact, I think it was IBM's system is like 99.8% accurate on common white face men versus 60% accurate, 65% accurate on dark-skinned women. So it's like, what is that, like 30 or 40 times worse for black women versus white men. And this is really important because for Kiva, black women are, perhaps the most common user base for their microlending platform. So Melissa, after taking our course and again working her ass off and being super intense in her study and her work, won this $1 million AI challenge for her work for Kiva. Karthik did our course and realized that the thing he wanted to do wasn't at his company, it was something else, which is to help blind people to understand the world around them, so he started a new startup. You can find it now, it's called Envision. You can download the app, you can point your phone at things, and it will tell you what it sees. And I actually talked to a blind lady about these kinds of apps the other day, and she confirmed to me this is a super useful thing for visually disabled users. And it's the level that you can get to with the content that you're going to get over these 7 weeks and with this software can get you right to the cutting edge in areas you might find surprising. For example, I helped a team of some of our students and some collaborators on actually breaking the world record for training. Remember I mentioned the ImageNet dataset? Lots of people want to train on the ImageNet dataset. We smashed the world record for how quickly you can train it. We use standard AWS cloud infrastructure, cost of $40 of compute to train this model using, again, FastAI library, the techniques that we learn in this course. So it can really take you a long way. So don't be kind of put off by this, what might seem pretty simple at first. We're going to get deeper and deeper. You can also use it for other kinds of passion project. So Helena Sarin, actually, you should definitely check out her Twitter account, Flagalista. This art is basically a new style of art that she's developed, which combines her painting and drawing with generative adversarial models to create these extraordinary results. And so I think this is super cool. I mean, she's not a professional artist. She is a professional software developer, but she just keeps on producing these beautiful results. And when she started, her art had not really been shown anywhere or discussed anywhere. Now there's recently been some quite high-profile articles describing how she is creating a new form of art. Again, this has come out of the FastAI course that she developed these skills. Or equally important, Brad Kensler, who figured out how to make a picture of Kanye out of pictures of Patrick Stewart's head. Also something you will learn to do if you wish to. This particular type of what's called style transfer was a really interesting tweak that allowed him to do some things that hadn't quite been done before. And this particular picture helped him to get a job as a deep learning specialist at AWS. So there you go. Another interesting example, another alumni actually worked at Splunk as a software engineer, and he designed an algorithm after like lesson 3, which basically turned out at Splunk to be fantastically good at identifying fraud. We'll talk more about it shortly. If you've seen Silicon Valley, the HBO series, the Hot Dog Not Hot Dog app, that's actually a real app you can download, and it was actually built by Tim Onglade as a FastAI student project. So there's a lot of cool stuff that you can do. Yes, it was Emmy nominated. So I think we only have one Emmy nominated FastAI alumni at this stage, so please help change that. All right. The other thing, is the forum threads can kind of turn into these really cool things. So Francisco, who's actually here in the audience, he's a really boring McKinsey consultant like me, right? So Francisco and I both have this shameful past that we were McKinsey consultants, but we left and we're okay now. And he started this thread saying like, oh, this stuff we've just been learning about building NLP in different languages, let's try and do lots of different languages. And he started this thing called the Language Model Zoo. And out of that, there's now been an academic competition was won in Polish that led to an academic paper, Thai state-of-the-art, German state-of-the-art. Basically, students have been coming up with new state-of-the-art results across lots of different languages, and this all is entirely being done by students working together through the forum. So please, get on the forum, but don't be intimidated, Because remember, a lot of the, everybody you see on the forum, the vast majority post all the damn time, right? They've been doing this a lot, and they do it a lot of the time, and so at first it can feel intimidating because it can feel like you're the only new person there. But you're not, right? All of you people in the audience, everybody who's watching, everybody who's listening, you're all new people, right? And so when you just get out there and say like, okay, all you people getting new state-of-the-art results in German language modeling, I can't start my server. I try to click the notebook and I get an error. What do I do? People will help you. Okay, just make sure you provide all the information. This is the, I'm using Paperspace. This was the particular instance I tried to use. Here's a screenshot of my error. People will help you. Okay, or if you've got something to add. So if people are talking about crop yield analysis and you're a farmer and you think, oh, I've got something to add, so please mention it. Even if you're not sure it's exactly relevant, it's fine. Just get involved. And because remember, everybody else on the forum started out also intimidated, right? We all start out not knowing things. And so just get out there and try it. Okay, so let's get back and do some more coding. Yes, Rachel, do we have some questions?
Yeah, there's just a question from earlier about why you're using ResNet as opposed to Inception.
So the question is about this architecture. So there are lots of architectures to choose from, and it would be fair to say there isn't one best one. But if you look at things like the Stanford Dawnbench benchmark for ImageNet classification, you'll see in first place and second place and third place and fourth place is FastAI, Jeremy Howard from FastAI, Jeremy Howard, FastAI, Yaroslav's from the Department of Defense Innovation Team, Google, ResNet, 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 ResNet. ResNet's good enough, okay? So it's fine. There are other architectures. The main reason you might want a different architecture is if you want to do edge computing, so if you want to create a model that's going to sit on somebody's mobile phone. Having said that, even there, most of the time I reckon the best way to get a model onto somebody's mobile phone is to run it on your server and then have your mobile phone app talk to it. It really makes life a lot easier and you get a lot more flexibility. But if you really do need to run something on a low-powered device, then there are some special architectures for that. So the particular question was about Inception. That's another architecture which tends to be pretty memory intensive ResNet. So Inception tends to be pretty memory intensive, but it's okay. It's also it's not terribly resilient. One of the things we try to show you is stuff which just tends to always work, even if you don't quite tune everything perfectly. So ResNet tends to work pretty well across a wide range of different kind of details around choices that you might make. So I think it's pretty good. So we've got this trained model, and so what's actually happened, as we'll learn, is it's basically creating a set of weights. If you've ever done anything like linear regression or logistic regression, you'll be familiar with coefficients. We basically found some coefficients and parameters that work pretty well, and it took us 1 minute and 56 seconds. So if we want to start doing some more playing around and come back later, we probably should save those weights so we can save that 1 minute and 56 seconds. So you can just go learn.save and give it a name. Okay. It's going to put it in a model subdirectory in the same place the data came from. So if you save different models for different data bunches from different data sets, they'll all be kept separate, so don't worry about it. All right, so we talked about how the most important things are how to learn what goes into your model, what comes out. We've seen one way of seeing what goes in. Now let's see what comes out. Okay, so this is the other thing you need to get really good at. So to see what comes out, we can use this class called classification interpretation. And we're going to use this factory method from learner. So we pass in a learn object. So remember, a learn object knows two things. What's your data? And what is your model? It's now not just an architecture, but it's actually a trained model inside there. And that's all the information we need to interpret that model. So we just pass in the learner, and we now have a classification interpretation object. And so one of the things we can do, and perhaps the most useful things to do, is called plot top losses. So we're going to be learning a lot about this idea of loss functions shortly. But in short, a loss function is something that tells you how good was your prediction. And so specifically that means if you predicted one class of cat with great confidence, you said, I am very, very sure that this is a Burman, but actually you were wrong, then that's going to have a high loss because you were very confident about the wrong answer. Okay, so that's what it basically means to have a high loss. So by plotting the top losses, we're going to find out what were the things that we were the most wrong on, or the most confident about but we got wrong. So you can see here, it prints out 3 things. German Shorthead, 4 things. Beagle, 7.04, 0.92. Well, what do they mean? Perhaps we should look at the documentation. So we've already seen help, right? And help just prints out a quick little summary. But if you want to really see how to do something, use doc. And doc tells you the same information as help, but it has this very important thing, which is show in docs. So when you click on show in docs, it pops up the documentation for that method or class or function or whatever. It starts out by showing us the same information about what are the parameters it takes, along with the doc string, but then tells you more information. So in this case, amongst other things, it tells me the title of each shows the prediction, the actual, the loss, and the probability that was predicted. So for example, and you can see there's actually some code you can run. So the documentation always has working code. And so in this case, it was trying things with handwritten digits. And so the first one, it was predicted to be a 7. It was actually a 3. The loss is 5.44. And the probability of the actual class was 0.07. Okay, so we did not have a high probability associated with the actual class. I can see why it thought this was a 7, but nonetheless it was wrong. So this is the documentation, okay? And so this is your friend when you're trying to figure out how to use these things. The other thing I'll mention is if you're a somewhat experienced Python programmer, you'll find the source code of FastAI really easy to read. We try to write everything in just a small number of, much less than half a screen of code, generally 4 or 5 lines of code. If you click source, you can jump straight to the source code, right? So here is the plot top losses. And this is also a great way to find out how to use the FastAI library, because every line of code here, nearly every line of code is calling stuff from the FastAI library. Okay? So don't be afraid to look at the source code. I've got another really cool trick about the documentation that you're going to see a little bit later. Okay, so that's how we can look at these top losses, and these are perhaps the most important image classification interpretation tool that we have, because it lets us see what are we getting wrong. And quite often, like in this case, if you're a dog and cat expert, you'll realize that the things it's getting wrong are breeds that are actually very difficult to tell apart, and you'd be able to look at these and say, oh, I can see why it got this one wrong. Okay? So this is a really useful tool. Another useful tool, kind of, is to use something called a confusion matrix, which basically shows you for every actual type of dog or cat, how many times was it predicted to be that dog or cat. But unfortunately, in this case, because it's so accurate, this diagonal basically says, oh, it's pretty much right all the time. And you can see there's some slightly darker ones, like a 5 here, but it's really hard to read exactly what that combination is. So what I suggest you use is, instead of, if you've got lots of classes, don't use a confusion matrix. But this is my favorite named function in FastAI. I'm very proud of this. You can call most confused. And most confused will simply grab out of the confusion matrix the particular combinations of predicted and actual that it got wrong the most often. So in this case, the Staffordshire Bull Terrier was what it should have predicted, and instead it predicted an American Pit Bull Terrier, and so forth. It should have predicted a Siamese and actually predicted Burman. That happened 4 times. this particular combination happens 6 times. So this is, again, a very useful thing, because you can look and you can say, like, with my domain expertise, does it make sense that that would be something that was confused about? So these are some of the kinds of tools you can use to look at the output. Let's make our model better. So how do we make the model better? We can make it better using fine-tuning. So far we fitted 4 epochs, and it ran pretty quickly. And the reason it ran pretty quickly is that there was a little trick we used. These deep learning models, these convolutional networks, they have many layers. We'll learn a lot about exactly what layers are, but for now, just know it goes through computation. What we did was we added a few extra layers to the end, and we only trained those. We basically left most of the model exactly as it was. So that's really fast. And if we're trying to build a model of something that's similar to the original pre-trained model, so in this case similar to the ImageNet data, that works pretty well. But what we really want to do is actually go back and train the whole model. So this is why we pretty much always use this 2-stage process. So by default, when we call fit or fit one cycle on a conv learner, it'll just fine-tune these few extra layers added to the end, and it'll run very fast. It'll basically never overfit. But to really get it good, you have to call unfreeze. And unfreeze is the thing that says, please train the whole model. And then I can call fit one cycle again, and the error got much worse. Okay, why? In order to understand why, we're actually going to have to learn more about exactly what's going on behind the scenes. So let's start out by trying to get an intuitive understanding of what's going on behind the scenes. And again, we're going to do it by looking at pictures. We're going to start with this picture. These pictures come from a fantastic paper by Matt Zeiler, who nowadays is CEO of Clarify, which is a very successful computer vision startup, and his supervisor of his PhD, Rob Fergus. And they created a paper showing how you can visualize the layers of a convolutional neural network. So a convolutional neural network will learn mathematically about what the layers are shortly, but the basic idea is that your red, green, and blue pixel values, that are numbers from 0 to 255, go into a simple computation, the first layer, and something comes out of that, and then the result of that goes into a second layer, and the result of that goes into a third layer, and so forth. And there can be up to 1,000 layers of a neural network. ResNet 34 has 34 layers, ResNet 50 has 50 layers. But let's look at layer 1. There's this very simple computation. It's a convolution. If you know what they are, we'll learn more about them shortly. What comes out of this first layer? Well, we can actually visualize the specific coefficients, the specific parameters, by drawing them as a picture. There's actually a few dozen of them in the first layer, so we won't draw all of them, but let's just look at 9 at random. So here are 9 examples of the actual coefficients from the first layer. And so these operate on groups of pixels that are next to each other. And so this first one basically finds groups of pixels that have a little diagonal line in this direction. This one finds diagonal lines in the other direction. This finds gradients that go from yellow to blue in this direction. This one finds gradients that go from pink to green in this direction, and so forth. And so they're very, very simple little filters. That's layer 1 of a ImageNet pre-trained convolutional neural net. Layer 2 takes the results of those filters and does a second layer of computation. And it allows it to create, so here are 9 examples of kind of a way of visualizing this, one of the second layer features. And you can see it's basically learned to create something that looks for corners, top left corners. And this one has learned to find things that find right-hand curves. And this one has learned to find things that find little circles. Right? So you can see how layer 2, like this is the easiest way to see it. In layer 1, we have things that can find just one line. In layer 2, we can find things that have 2 lines joined up, or one line repeated. If you then look over here, these 9 show you 9 examples of actual bits of actual photos that activated this filter a lot. Right? So in other words, this little bit of function, math function here, was good at finding these kind of window corners and stuff like that. This little circly one was very good at finding bits of photos that had circles in. Okay, so this is the kind of stuff you've got to get a really good intuitive understanding for. It's like the start of my neural net's going to find simple, very simple gradients and lines. The second layer can find very simple shapes. The third layer can find combinations of those. So now we can find repeating patterns of two-dimensional objects, or we can find kind of things that lines that join together, or we can find, well, what are these things? Well, let's find out. What is this? Let's go and have a look at some bits of picture that activated this one highly. Oh, mainly they're bits of text, although sometimes windows. So it seems to be able to find kind of like repeated horizontal patterns. And this one here seems to be able to find kind of edges of fluffy or flowery things. This one here is kind of finding geometric patterns. Right? So layer 3 was able to take all the stuff from layer 2 and combine them together. Layer 4 can take all the stuff from layer 3 and combine them together. By layer 4 we've got something that can find dog faces. And let's see what else we've got here. Yeah, various kinds of, oh, here we are, bird legs. So you kind of get the idea. And so by layer 5, we've got something that can find the eyeballs of birds and lizards, or faces of particular breeds of dogs, and so forth. So you can see how by the time you get to layer 34, you can find specific dog breeds and cat breeds, right? This is kind of how it works. So when we first fine-tuned that pre-trained model, we kept all of these layers that you've seen so far. And we just trained a few more layers on top of all of those sophisticated features that had already been created. Right? And so now we're fine-tuning, we're going back and saying, let's change all of these. We'll start with them where they are, right? But let's see if we can make them better. Now, it seems very unlikely that we can make these layer 1 features better. Like, it's very unlikely that the definition of a diagonal line is going to be different when we look at dog and cat breeds versus the ImageNet data that this is originally trained on. So we don't really want to change layer 1 very much, if at all. Whereas the last layers, this thing of like types of dog face, seems very likely that we do want to change that. Right? So you kind of want this intuition, this understanding that the different layers of a neural network represents different levels of kind of semantic complexity. So this is why our attempt to fine-tune this model didn't work, is because we actually, by default, it trains all the layers at the same speed, right? Which is to say it'll update those like things representing diagonal lines and gradients just as much as it tries to update the things that represent the exact specifics of what an eyeball looks like. So we have to change that. Okay? And so to change it, we first of all need to go back to where we were before. Okay? We just broke this model, right? It's much worse than it started out. So if we just go load, this brings back the model that we saved earlier. Remember we saved it as stage 1? Okay? So let's go ahead and load that back up. So that's now, our model's back to where it was before we killed it. And let's run Learning Rate Finder. We'll learn about what that is next week. But for now, just know this is the thing that figures out what is the fastest I can train this neural network at without making it zip off the rails and get blown apart. Okay, so we can call learn.lrfind, and then we can go learn.recorder.plot, and that will plot the result of our LR finder. And what this basically shows you is there's this key parameter that we're going to learn all about called the learning rate. And the learning rate basically says how quickly am I updating the parameters in my model. And you can see that what happens is, as this bottom one here shows me what happens as I increase the learning rate, and this one here shows what's the result, what's the loss. And so you can see once the learning rate gets past 10 to the negative 4, my loss gets worse. Okay? So it actually so happens, in fact I can check this, if I press Shift Tab here, my learning rate defaults to 0.003. So my default learning rate is about here. So you can see why our loss got worse, right? Because we're trying to fine-tune things now, we can't use such a high learning rate. So based on the learning rate finder, I tried to pick something, well before it started getting worse. So I decided to pick 1e neg 6. So I decided I'm going to train at that rate. But there's no point training all the layers at that rate, because we know that the later layers worked just fine before when we were training much more quickly. Again, it was the default, which was, to remind us, 0.003. So what we can actually do is we can pass a range of learning rates to learn.fit. And we do it like this. You use this keyword in Python. You may have come across it before. It's called slice. And that can take a start value and a stop value. And basically what this says is train the very first layers at a learning rate of 1e neg 6, and the very last layers at a rate of 1e neg 4, and then kind of distribute all the other layers across that, between those two values equally. So we're going to see that in a lot more detail, right? But basically, for now, this is kind of a good rule of thumb, is to say after you unfreeze, so this is the thing that's going to train the whole thing, pass a max learning rate parameter, pass it a slice, make the second part of that slice about 10 times smaller than your first stage. So our first stage defaulted to about 1e neg 3, so let's use about 1e neg 4. And then this one should be a value from your learning rate finder, which is well before things started getting worse. And you can see things are starting to get worse maybe about here. So I picked something that's at least 10 times smaller than that. So if I do that, then I get 0.05788. So I don't quite remember what we got before. Yeah, a bit better, right? So we've gone down from a 6.1% to a 5.7%. So that's about a 10 percentage point relative improvement with another 58 seconds of training. So I would perhaps say for most people, most of the time, these two stages are enough to get pretty much a world-class model. You won't win a Kaggle competition, particularly because now a lot of FastAI alumni are competing on Kaggle, and this is the first thing that they do. But, in practice, you'll get something that's, about as good in practice as the vast majority of practitioners can do. We can improve it by using more layers, and we'll do this next week by basically doing a ResNet 50 instead of a ResNet 34. You can try running this during the week if you want to. You'll see it's exactly the same as before, but I'm using ResNet 50 instead of ResNet 34. What you'll find is it's very likely if you try to do this, you will get an error. And the error will be your GPU has run out of memory. And the reason for that is that ResNet 50 is bigger than ResNet 34. And therefore it has more parameters, and therefore it uses more of your graphics card's memory, which is totally separate to your normal computer RAM. This is GPU RAM. If you're using the kind of default Salamander, AWS, and so forth suggestion, then you'll be having 16 gig of GPU memory. The card I use most of the time has 11 gig of GPU memory. The cheaper ones have 8 gig of GPU memory. And that's kind of the main range you tend to get. If yours has less than 8 gig of GPU memory, it's going to be frustrating for you. Anyway, so you'll be somewhere around there. And it's very likely that when you try to run this, you'll get an out-of-memory error. And that's because it's just trying to do too many parameter updates for the amount of RAM you have. And that's easily fixed. This image data bunch constructor has a parameter at the end, batch size, BS for batch size. And this basically says, how many images do you train at one time? If you run out of memory, just make it smaller. Okay? So this worked for me on an 11 gig card. It probably won't work for you if you've got an 8 gig card. If you do, just make that 32. It's fine to use a smaller batch size. It might take a little bit longer. That's all. Okay? If you've got a bigger, like a 16 gig, you might be able to get away with 64. Okay? So that's just one number you'll need to try during the week. And again, we feed it for a while, and we get down to a 4.4% error rate. So this is pretty extraordinary. I was pretty surprised because, when we first did in the first course just cats versus dogs, we were kind of getting somewhere around a 3% error for something where you've got a 50% chance of being right, and the two things look totally different. So the fact that we can get a 4.4% error for such a fine-grained thing, it's quite extraordinary. In this case, I unfroze it and fitted a little bit more, went from 4.4 to 4.35, tiny improvement. Basically, ResNet 50 is already a pretty good model. It's interesting because, again, you can call most confused here, and you can see the kinds of things that it's getting wrong. And I actually, depending on when you run it, you're going to get slightly different numbers, but you'll get roughly the same kinds of things. So quite often I find that Ragdoll and Berman are things that it gets confused, and I actually have never heard of either of those things. So I actually looked them up on the internet, and I found a page on the cat site called "Is This a Berman or a Ragdoll?" And there is a long thread of cat experts like arguing intensely about which it is. So I feel fine that my computer had problems. I found something similar. I think it was this Pit Bull versus Staffordshire Bull Terrier. Apparently the main difference is like the particular kennel club guidelines as to how they are assessed. But some people think that one of them might have a slightly redder nose. So this is the kind of stuff where actually, even if you're not a domain expert, it helps you become one, right? Because I now know more about which kinds of pet breeds are hard to identify than I used to. So model interpretation works both ways. So what I want you to do this week is to run this notebook, make sure you can get through it. But then what I really want you to do is to get your own image data set. And actually, Francisco, who I mentioned earlier, he started the Language Stew model thread, and he's now helping to TA the course. He's actually putting together a guide that will show you how to download data from Google Images, so you can create your own data set to play with. But before I do, I want to...
There's also one more question.
Okay, I'll come back to that in a moment. Before I do, I want to show you how to create labels in lots of different ways. Because your data set, wherever you get it from, won't necessarily be that kind of regex-based approach. It could be in lots of different formats. So to show you how to do this, I'm going to use the MNIST sample. MNIST is pictures of hand-drawn numbers. Just because I want to show you different ways of creating these data sets. The MNIST sample basically looks like this. So I can go path.ls, okay? And you can see it's got a training set and a validation set already. So basically the people that put together this data set have already decided what they want you to use as a validation set. Okay, so if we go path/train.ls, you'll see there's a folder called 3 and a folder called 7. Right? Now this is really, really common way to give people labels. It's basically to say, oh, everything that's a 3, I'll put in a folder called 3. Everything that's a 7, I'll put in a folder called 7. Right? This is often called an ImageNet style data set, because this is how ImageNet is distributed. So if you have something in this format where the labels are just whatever the folder's called, you can say from folder. Okay? And that will create an image data bunch for you. And as you can see, 3, 7, it's created the labels just by using the folder names. Another possibility, and as you can see, we can train that, get 99.55% accuracy, blah, blah, blah. Another possibility, and for this MNIST sample I've got both, it might come with a CSV file that would look something like this. For each file name, what's its label? Now in this case, the labels aren't 3 or 7, they're 0 or 1, which is basically, is it a 7 or not? Right? So that's another possibility. So if this is how your labels are, you can use from CSV. And if it's called labels.csv, you don't even have to pass in a file name. If it's called anything else, then you can pass in the CSV labels file name. Okay, so that's how you can use a CSV. Again, there it is. This is now, is it a 7 or not? Another possibility, and then you can call data.classes to see what it found. Another possibility is, as we've seen, is you've got paths that look like this. And so in this case, this is the same thing. These are the folders, right? I could actually grab the label by using a regular expression. And so here's the regular expression. So we've already seen that approach. And again, you can see data.classes has found it. So what if it's something that's in the file name or the path, but it's not just a regular expression, it's more complex? You can create an arbitrary function that extracts a label from the file name or path. And in that case, you would say from name and function. Another possibility is that you need something even more flexible than that. And so you're going to write some code to create an array of labels. And so in that case, you can just pass in from lists. So here, I've created an array of labels. Here are my labels. Here's from lists. Okay, and then I just pass in that array. So you can see there's lots of different ways of creating labels. So during the week, try this out. Now, you might be wondering, how would you know to do all these things? Like, where am I going to find this kind of information, right? How do you possibly know to do all this stuff? So I'll show you something incredibly cool. Let's grab this function. And do you remember, to get documentation, we type doc. And here's the documentation for the function, and I can click Show in Docs. And it pops up the documentation. So here's the thing. Every single line of code I just showed you, I took it this morning and I copied and pasted it from the documentation. So you can see here the exact code that I just used. So the documentation for FastAI doesn't just tell you what to do, but step to step how to do it. And here is perhaps the coolest bit. If you go to FastAI, FastAI_docs, and click on docs source, it turns out that all of our documentation is actually just Jupyter Notebooks. So in this case, I was looking at vision.data. So here is the vision.data notebook. You can download this repo, you can git clone it, and if you run it, you can actually run every single line of the documentation yourself. Okay, so all of our docs is also code. And so like this is the kind of the ultimate example to me of experimenting, right? Is that you can now experiment, and you'll see in GitHub it doesn't quite render properly because GitHub doesn't quite know how to render notebooks properly. But if you git clone this and open it up in Jupyter, you can see it. And so now, anything that you read about in the documentation, nearly everything in the documentation has actual working examples in it with actual data sets that are already sitting in there in the repo for you. And so you can actually try every single function in your browser. Try seeing what goes in and try seeing what comes out.
There's a question, will the library use multi-GPU in parallel by default?
The library will use multiple CPUs by default, but just one GPU by default. We probably won't be looking at multi-GPU until part 2. It's easy to do, and you'll find it on the forum, but most people won't be needing to use that now.
And the second question is whether the library can use 3D data, such as MRI or CAT scan.
Yes, it can, and there is actually a forum thread about that already. Although that's not as developed as 2D yet, but maybe by the time the MOOC is out, it will be. So before I wrap up, I'll just show you an example of the kind of interesting stuff that you can do by doing this kind of exercise. Remember earlier I mentioned that one of our alums who works at Splunk, which is a NASDAQ-listed, big, successful company, created this new anti-fraud software. This is actually how he created it as part of a FastAI Part 1 class project. He took the telemetry of users who had Splunk Analytics installed and watched their mouse movements, and he created pictures of the mouse movements. He converted speed into color and right and left clicks into splodges. He then took the exact code that we saw with an earlier version of the software and trained a CNN in exactly the way we saw, and used that to train his fraud model. So he basically took something which is not obviously a picture, and he turned it into a picture, and got these fantastically good results for a piece of fraud analysis software. So it pays to think creatively. So if you're wanting to study sounds, a lot of people that study sounds do it by actually creating a spectrogram image and then sticking that into a ConvNet. So there's a lot of cool stuff you can do with this. So during the week, get your GPU going, try and use your first notebook, make sure that you can use lesson 1 and work through it, and then see if you can repeat the process on your own data set. Get on the forum and tell us any little success you had. It's like, oh, I spent 3 days trying to get my GPU running and I finally did. Any constraints that you hit, try it for an hour or 2, but if you get stuck, please ask. And if you're able to successfully build a model with a new data set, let us know. And I will see you next week.